So this is number 3 from the assignment, and they do give us a function, which I have written right there, but what's most important to us right now is this graph that they provided for us, because they said determine the open intervals on which the graph is concave up or concave down. So I'm going to start by looking for any kind of segments that it looks concave up. So this is kind of a rough estimate. That's all your book really requests. Right here, I'm going to draw a line. That is an example of concave up. So I'm going to go ahead. These are going on forever. So from negative infinity to, and then I'm going to just approximate negative 3 for conc up. Okay. From about 3 and then onward, once again, that's another conc up. It doesn't necessarily have to go up in a loop, you know. It's still just, this is a portion that is conc up. It's where our rates are slowly increasing. From 3 to infinity is also conc up. Okay, and I'll change right here. This is where we have something of conc down, and those would have been our inflection points. But they don't ask for that. So from negative 3 to 3, we're conc or cave down. Concavity down. That's it. Alright, the next problem from the assignment that we're going to do is number 13. And the directions are to find the points of inflection and discuss the concavity of the graph of the function. I'm going to kind of just list out our overall objectives of this problem. First, we need to find our inflection points, so I'll write that. What are those? And then where is it concave up and concave down? That would be the discussion of the concavity of it. Alright, so I'm just going to kind of put a box in here for now. That is our unknown, and that is our overall objective of this problem, given the directions. So I'm going to change colors now, and we're going to start by first locating our inflection points. So when we're looking at the inflection points, what we're going to have to look at is the first derivative and then the second derivative to determine what the first derivative is doing, so what the rate of changes are doing. So I'm going to go ahead and derive this, and then we're going to have to derive again. Alright, so since inflection points are kind of like the critical points of our first derivative, what we're going to be doing is setting this equal to 0, because then we're going to be finding where are the humps and our valleys in the first derivative. So we're going to have to find for what values of x is our second derivative equal to 0. When you simplify this all out, what you're going to get is 2 over the square root of 3, and they don't even bother to rationalize that in the back of your book, so I won't either. But what I am going to tell you is this is approximately plus minus 1.15, and I'll be using that here in a little bit. But now that I've found the x values of my inflection points, now once again, these are the points where it's going to be switching from concave up to concave down or vice versa. So I have found the x values of those inflection points. One of them is plus 2 over the square root of 3. I didn't necessarily have to write that plus. And then the other one is going to be negative 2 over the square root of 3. So knowing that, what I need to do in order to get what is the actual point of inflection, I'm going to have to take these values right here, and in order to get the y values, sub them into my original function. So I'll do that right here. F of, and then 2. And when you do this on your calculator, what I do get is negative 20 over 9, which is approximately negative 2.22, but this is for now what I'm going to be keeping. So here, get negative 20 over 9, and I will say this is an even function, so go ahead and plug in negative 2 over the square root of 3, but we're going to get the same answer because these are all even exponents, so we get negative 20 over 9 here as well. Try it if you don't believe me. Okay. So there we have our inflection points. Alright, now what we need to discuss is where is it concave up and concave down. Once again, we're going to be trying to figure out where is our first derivative increasing and where is it decreasing, because that will tell us where it's concave up and concave down. So in order to do that, what we're going to do is, much like we did before, I'm going to be setting up a sine line just like we did before, but testing the second derivative. So here what I have, I'm going to put on, this is where I'm going to use my estimated values. These are the inflection points. These are those key points that we just found. So I'm going to test points on this number line. In this interval right here, what I can tell you is we're going to be looking at the interval from negative infinity up until negative 2 over the square root of 3. And that is either going to have a negative or positive second derivative value. If it's negative, it's concave down. If it's positive, it's concave up. We're also going to have to test this interval right here. Alright, so I'm going to go ahead and test here negative 2. And once again, we're plugging this into our second derivative because that's what's going to be telling us when it's concave up or concave down. So I am going to be plugging it right into here. Regardless of what the actual value is, what I'm most interested in is this is going to be positive. So I'm going to go ahead and put a positive sign there because that's going to tell me this is concave up. I'm just going to write conc up. Alright, and then f prime, double prime of, I'm going to test in our 0. That is going to be negative. So I'm going to put my negative sign in there. This is going to be negative. So therefore, this tells me I have a conc down interval. And lastly, I'm just going to plug in maybe 2. You could have plugged in anything to the right of that 1.15, but I'll plug in 2. See, once again, that's going to be positive. So here, that last one, this is conc up as well. So we have completed this task, and so you can switch between the two of them, but what I want you to look at visually is there's that approximately negative 1.15. Here's the other approximate positive 1.15, and then you can see here how it is almost negative 20 over 9, or in other words, negative 2.22. But what we can see here is first it was concave up, then concave down, concave up. Alright, we're going to do number 33 now. It is a rational function, and I have been doing a lot of the times an example of a polynomial and an example of a rational function in my videos so far, because I hope you're going to start to see the difference between the process of rational and process of polynomials. There is always kind of this piece that you have to be careful of with rationals. So I have gone ahead and condensed this into one fraction. Now I'm looking at x squared plus 4 over x. And what we're supposed to be doing with this is finding the relative extrema and then use the second derivative test where applicable. So basically what we have to find is where are there any relative minimums and where are there any relative maximums. What we're going to do is be using the second derivative to find out, is it a relative maximum or is it a relative minimum that we find when we're looking at these critical points. You've had one way of doing this from our previous 5.3, but this is just going to be a different kind of way. I did not go over the second derivative test very much. It is in your book, so you can look up other examples of it. But really what I just want you to learn is, can you on your own kind of apply the idea of concavity and how that would relate to relative extrema. So for this first thing, what I'm going to have to do is find our critical points. So I am going to derive my function. Get low, d high. What I get then is f prime of x is equal to x squared, 1x squared, minus 4. Don't forget to distribute that subtraction all over x squared. Remember, with critical values, what we're trying to figure out is where is the first derivative either equal to 0 or undefined. So with rational functions, that's where it really becomes necessary to set your, not only the top equal to 0, because that's when the overall function would equal 0, but when the bottom is also equal to 0, because that's when this function right here would be equal to undefined. So critical points, we find them by setting f prime of x equal to either 0 or undefined. Those are the points that something interesting with our graph is occurring. And those are the points where it could switch from increasing to decreasing. So therefore we could get our some sort of extrema possibly. So I'm going to set the top, begin by setting the top equal to 0. You need to set the bottom equal to 0. So these are our critical points. Now that I have found the location, the x values of my critical points, what we're going to be doing with the second derivative test is it's really trying to say, well, at those points, is it going to be a negative or positive second derivative value? Because if you knew that these laid in an interval where it was concave up, then you would know that these critical points are going to be some sort of negative value. If you knew that it was lying in a point or in an interval on our function that is concave down, then you would know it's a relative maximum. So what I'm going to be doing is I'm going to be taking each one of these x values and plugging them into my second derivative. So first I need to find my second derivative. F double prime of x is equal to, and these will cancel out, so what I get is f double prime of x is equal to 8 over x cubed. And so what I'm going to be doing with this is I'm going to be plugging in these values, because if when I plug in, for example, now I want to scroll this down a little bit, f double prime of 2 is going to be equal to 8 over 2 to the third, which is just going to be 1, but once again that's positive. What this is telling us is when we look at that critical value x equaling 2, when you consider that when you plug that into the second derivative it's equaling to a positive, that means that it's lying within some sort of positive second derivative, which is saying that it's concave up. So what that just told you is that this is a relative minimum. So at x equals 2, we have some sort of minimum. Okay. And then what I'm going to be checking is what's happening at x equals negative 2. Is that laying in a concave up or a concave down section? So I'm going to plug in f prime of negative 2 equals, and what you're going to notice is that's going to be negative when you plug that in. So this is going to be, so careful, once again, this is meaning that it's concave down, so that translates to x equaling negative 2, that critical value as being some sort of maximum. What I'm also going to do is plug in f prime of 0, and right here it's an undefined. So being that it's an undefined, it's not laying in some sort of concave up, concave down, something else is happening here. So at x equals 0, we actually don't have critical point because it doesn't occur. It's not happening there. So what we can just look at as these 2 points as our minimum and maximum. So finally, what I'm going to do is I'm going to take those x values and I'm going to say my relative minimum. My minimum is occurring at 2, comma, and then I'm going to plug it into my original equation. So 2, 4. And my maximum is going to occur at negative 2. So I'm going to be taking this and plugging it into here again to find out what my y value is. Negative 2 plus negative 2 is negative 4. Alright, so there is the objective I was looking to reach. So now what I'm going to go ahead and do is point to you. If you were to look here on, this is the actual graph, what we found was that 2, 4 lied in a concave up section, and negative 2, negative 4, that was a critical value that laid in a concave down section. So there is our relative maximum, relative minimum.